1862, Northumberland, and the winding engine at New Hartley Colliery is already turning when the morning shift steps into the cage. The drum is cast iron, nearly 12 feet across, and the wire rope coiled onto it is thicker than a grown man's wrist. The engine house smells of hot tallow and coal smoke, and something older beneath both the mineral exhalation of a shaft sunk more than 600 feet into the earth. The floor of the house vibrates at a frequency too low to hear. Men feel it in the arches of their feet. They have felt it every working morning of their adult lives, and they do not notice it anymore, which is exactly how things stood on the morning of January the 16th. The banksman at the surface calls the signal. 3 bells. The engineman advances the throttle. The drum rotates. 204 men and boys ride down into the dark in the cage, and in the corves descending alongside it, the way they always do. Their bodies pressed together in the blackness, boots on iron, the rope above them taut and reliable. That is the last ordinary moment in the history of New Hartley. What happens next? The snapping of a cast iron beam? The collapse of the headgear? The sealing of the only shaft is not a failure of the winding engine itself, but the catastrophe it produces belongs entirely to the logic of the machine's world, a world built on the premise that a single rope through a single shaft is sufficient passage between the living and the dead. To understand why that logic existed, why it seemed not just acceptable but rational for the better part of a century, you have to go back to the problem that created the winding engine in the first place. Back to the moment when coal became the appetite of an industrializing civilization, and the earth simply refused to give it up without cost. By the early 18th century, the collieries of Northumberland and Durham had already exhausted the shallow measures. Shafts that once ran 150 feet had been worked to nothing. The seams men needed were deeper, 300 feet, 400, and the numbers kept growing, and at those depths, the horse gin, that ancient circular contraption of beam and horse and rope, reached the hard boundary of its physics. A horse produces roughly 1 horsepower. A single gin could raise perhaps 40 pounds of coal per minute from 300 feet, and at that rate the economics of deep mining were simply impossible. The owners understood the arithmetic. The horses understood nothing except the circle they walked, but even they were being replaced not by a better horse, but by steam. James Watt's improvements to the Newcomen atmospheric engine in the 1760s and 1770s produced a machine that could do rotary work, continuous rotary work, and the colliery owners of the northeast coalfields grasped the implication immediately. By the 1790s, winding engines driven by steam were replacing horse gins at the major Northumberland and Durham pits. The transition was not gradual. It was a decision, made mine by mine, driven by the same calculation every time. Deeper coal, more coal, faster coal, and no animal alive could provide it. John Buddle, the most capable colliery viewer of his generation, overseeing operations across the northeast coalfields in the first decades of the 19th century, understood the winding engine as the central nervous system of any serious mine. Without it, depth was a ceiling. With it, depth became a resource. The engine Buddle and his contemporaries installed was conceptually simple. A steam cylinder driving a crank, the crank turning a drum, the drum winding or unwinding a rope, the rope raising or lowering a cage or a set of loaded corves. The early drums used flat hemp rope, which limited load. Wire rope, adopted progressively through the 1830s and 1840s, changed everything stronger, more consistent, capable of carrying far greater loads across far greater depths. The wire rope was itself a manufactured object of remarkable sophistication. Dozens of individual drawn steel wires twisted into strands, the strands twisted into the rope, each layer of twist running counter to the last, so that the whole assembly would not unravel under load. A good rope, properly maintained, could last years at moderate depths. At great depth, under repeated shock loading, it aged invisibly, its internal wires fatiguing in ways no surface inspection could detect until the moment of failure. And here is where the machine's first irony enters the story with the calm indifference of a mathematical fact. The larger and more powerful the winding engine became, the more energy it concentrated into that single rotating drum. A horse gin stored almost nothing stopped the horse. The rope stops. A steam winding engine with a 12-foot drum spinning at speed stored kinetic energy in the tens of thousands of foot-pounds, and that energy did not care about the intentions of the engineman who governed it. To address this, engineers added governor centrifugal devices that would theoretically cut steam supply if rotational speed exceeded a set threshold, and they added indicator boards, calibrated dials that showed the engineman where the cage was in the shaft at any moment. These were the safety systems. They worked most of the time, and their existence gave the owners and the regulators a language of reassurance. The machine had protections. The protections were documented. That was, for several decades, considered sufficient. By the 1840s and 1850s, the winding engine had spread to every significant coal field in Britain and had crossed the Atlantic to the hard rock mines of Pennsylvania, Michigan, and Virginia. It had crossed to the gold reefs of New South Wales and the copper lodes of South Australia. Everywhere the logic was the same: one shaft, one rope, one drum, one engineman. Mines Inspectorate reports from the 1850s, the first systematic records of shaft accidents in British collieries, noted overwinding incidents with a frequency that should have been alarming. A cage carried too far up the shaft by an engineman who misjudged his indicator, the rope snapping under the sudden arrest, the cage falling, men killed or maimed. The detaching hook was the engineering response, a device fitted above the cage that was supposed to release the rope automatically if the cage overshot the surface, allowing the cage to settle onto the headgear structure rather than being pulled through it. It was a genuine innovation. It was also a mechanism that required precise calibration, regular testing, and correct installation to function at all. And the Inspectorate's own reports across the 1850s and 1860s documented dozens of cases where detaching hooks had been set incorrectly, had not been tested within any reasonable interval, or had simply failed to trigger when the moment arrived. The system had a safety layer. The safety layer depended entirely on maintenance discipline that the economic logic of the mine consistently eroded. By 1870, there were more than 500 steam winding engines operating in the British coalfields alone. By 1890, the shafts they served had deepened substantially, 800 feet, 1,200 feet, and in South Africa, where the Witwatersrand gold rush of 1,886 began sinking reefs to previously unimagined depths, shafts would eventually reach more than a mile underground. The engine houses above those South African shafts were enormous brick structures, their interiors hot even in winter from the radiant heat of cylinder jackets and steam pipes, the air tasting of iron oxide and grease, the vibration through the concrete floor strong enough to blur a man's vision if he stood in the wrong place and looked at a fixed point. At those depths, the winding rope itself weighed tons before any cage or payload was attached. A rope of steel wire descending 3,000 feet and returning weighed more than the loaded cage it carried, and the dynamics of that rope, its elasticity, its resonant frequency under load, the shock wave transmitted through it when a cage was arrested, suddenly added layers of mechanical complexity that the original designs had never contemplated. The drum diameters grew to match. Engines of 1,000 horsepower and more became standard at the deepest South African gold mines by the turn of the 20th century. The engineman sitting at his controls was now governing a machine that could accelerate a fully loaded cage from rest to 30 miles per hour in a matter of seconds and bring it back to a precise stop within inches of the surface bank. Or fail to stop it, at which point the stored energy in the rotating drum was not a theoretical quantity, but a physical event. This is the second irony, and it is the one that the engineering profession understood perfectly in the abstract and managed imperfectly in practice. The feature that made the large winding drum reliable, its massive rotational inertia, which smoothed out load variations, prevented jerking, maintained steady rope tension across the full depth of the shaft, was the same feature that made it impossible to arrest quickly once control was lost. A small drum with little inertia could be braked hard and stopped in a few rotations. A 12-foot cast iron drum spinning at speed, with several tons of rope and cage in motion, would continue rotating for seconds after maximum braking was applied, and in a winding engine, seconds translated directly into feet of rope travel, and feet of rope travel at the top of the shaft translated into structural catastrophe. the engineman was not a passive observer of this process. He was its last control system. His hand on the throttle, his eye on the indicator board, his judgment about the slight lag between the board's reading and the cage's true position, these were the final barriers between a successful winding cycle and an overwinding event. The indicator board itself was a mechanical instrument, a dial whose needle was driven by a gear train connected to the drum shaft, calibrated at installation to show cage position against depth markings painted or stamped on the face. Over years of operation, the gears wore, the calibration drifted, and the discrepancy between what the board showed and where the cage actually was might amount to 10 feet or 20 manageable error at shallow depth, potentially lethal error in the final 50 feet of a fast wind. Enginemen who worked a single installation for years developed an almost proprioceptive understanding of their machine. They felt the load through the engine's behavior. They heard the sound of the rope on the drum change as the cage approached the surface. Some could read the engine's steam pressure gauge and the indicator simultaneously and adjust for the slight inaccuracy they knew their particular indicator carried on warm days versus cold. This expertise was real. It was also unreproducible, untransferable, and entirely invisible to the owners who depended on it. The colliery owners of the 1880s and 1890s were managing operations that had grown enormously in scale and complexity, and their relationship to safety was mediated almost entirely by accident, frequency, not by the accumulating stress cycles in aging rope, not by the calibration drift in indicator boards that had never been recertified, not by the quiet erosion of testing discipline for detaching hooks at installations where no accident had occurred in 15 years, and where testing meant downtime and downtime meant lost production. The HM Inspector of Mines' annual reports from this period document a pattern that, in retrospect, reads with the clarity of inevitability: minor overwinding incidents at a colliery, an inspector's recommendation for improved indicator maintenance or more frequent hook testing, acknowledgement from the owner, and then, months or years later, the next entry from the same colliery, or one structurally identical to it. Reports were filed. Recommendations were noted. The drums kept turning. At Sylfanid in South Wales, at the Universal Colliery in June of 1894, the winding apparatus was not the primary mechanism of death. An underground explosion claimed 290 lives, but the shaft and its hoisting system defined the rescue operation's speed and limits in ways that the subsequent inquest made plain. The infrastructure designed to move men efficiently in normal production became the bottleneck of disaster response. And the inquest documents of that period show inspectors repeatedly circling around the question of single-shaft operations without ever formally condemning them. The machine that worked was the machine that was trusted, and the machine that was trusted was the machine whose fundamental design assumptions went unexamined. The disaster that crystallized all of these forces most completely for the British mining public had already occurred at New Hartley in 1862, and it is worth dwelling on what actually happened there, because it is not quite the story most accounts tell. The winding engine itself did not fail. What failed was a 14-ton cast iron beam that was part of the pumping engine adjacent to the shaft, a beam that had been showing signs of wear, that operators had noted but not replaced, that broke under load and fell directly into the only shaft serving the colliery. 204 men and boys were underground. The cage could not reach them. The shaft was blocked. They died over the following days not from the initial impact, but from asphyxiation as the ventilation system, which also ran through the single shaft, failed. The coroner's inquest and the subsequent parliamentary inquiry produced extensive documentation. The condition of the beam had been observable. The risks of single-shaft operations had been raised previously in engineering circles. The men underground had worked in a system that offered them no second means of egress. What the inquiry produced in terms of legislation was the Coal Mines Regulation Act of 1862, which required all new mines to have two shafts separated by a sufficient distance to prevent a single event from blocking both. It was a meaningful reform. It was also a reform that applied to new mines, that exempted many existing operations for years, and that addressed the single-shaft problem without addressing the engineering assumptions built into the winding apparatus itself. The indicator boards kept their original calibration tolerances. The governor testing intervals remained advisory at many installations, The detaching hook remained a device whose function in a real overwinding event depended on conditions, hook setting, cage speed, rope elasticity at operating temperature that the routine inspection cycle did not reliably verify. The investigation, thorough by every standard of its era, had measured the specific catastrophe. It had not measured the system. This pattern legislation, following catastrophe, legislation addressing the specific rather than the structural, repeated itself across the following decades with the regularity of a mechanical process. Each major winding accident produced its inquest, its inspectorate report, its parliamentary question, its amendment to the Mines Regulation Acts. The Coal Mines Act of 1911, the most comprehensive mining safety legislation Britain had yet produced, mandated automatic overwinding protection devices at all winding installations, mechanical governors, and clutches that would trip without the engineman's intervention if the cage exceeded a set speed near the surface. Engineers, including W.C. Mountain and others working in the safety device field through the 1900s, had developed reliable automatic protection systems, and their adoption after 1911 was genuine progress. But adoption across the existing stock of several hundred winding installations was slow, contested, and expensive. Older collieries argued for exemptions. Equipment manufacturers quoted retrofit costs that owners translated directly into reduced margins. The Mines Inspectorate, with limited enforcement capacity spread across a vast industry, could not compel simultaneous compliance. Automatic devices were fitted. Overwinding accidents continued, at reduced frequency. For decades, the reform had entered the frame. The economics of the existing machine argued back, and the economics were not irrational. They were simply pointed at a different calculation than safety. What finally ended the steam winding engine was not safety legislation, but electricity. Through the 1920s and 1930s, electric winding engines began replacing steam installations at colliery after colliery across Britain, South Africa, and the American coalfields. Electric motors offered continuous variable speed control through the full winding cycle with a precision that steam throttle and valve systems could not match. They could be integrated directly with automatic speed-limiting circuits that did not require a separate mechanical governor to trip, but that were embedded in the motor control system itself, cutting power and applying brakes at preset approach speeds without any human intervention in the chain. The engineman remained at his controls, but the controls now included automatic systems that would override his judgment if his judgment failed. The thing that had been the system's fatal dependency, one man's trained instincts as the last barrier, was, for the first time, structurally removed from the failure pathway. The last operational steam winding engines at deep-shaft British collieries were retired through the 1950s and 1960s as the nationalized coal industry systematically modernized its plant. Some were preserved. The engine house at Beamish Museum in County Durham contains a preserved winding engine of the type that served the northeast coalfields for more than a century, its drum motionless, its rope coiled, its indicator board arrested at a reading that once told an engine man where his men were in the dark. The floor of the engine house no longer vibrates. There is no smell of hot tallow, no subsonic thrum through the timber, no sound of rope under load. The machine is cold. The men it once carried are long gone. And the silence, where the drum used to turn, is the exact measure of what the industry spent 100 years failing to build into the system while the machine was still alive. The certainty that no single moment of human error, no single point of mechanical failure, could seal the only passage between the men below and the world above.